Happy April Fool's Day. When I was on the receiving end of an April Fool's joke. Yeah, which is a good thing because April Fool's Day is pretty kind of neat.
What was the April Fool's?
Well, okay. In 1992, at Stanford, there was a controversy over the Stanford bookstore, which bookstores go at a very high price. Like executives were getting perks, like they can ride to the yacht and things like that, and there was a scandal. So in the student newspaper, there was an item saying that to make up for these past abuses, that bookstores could offer refunds and go to a bookstore. I actually went to a bookstore and almost could have put a talk with somebody when I realized, wait a minute, it's April 1st. Barely saved my phone. Okay. Now, okay, back to initial value problems. Okay. First, a quick item about a homework that's related to what I was just covering. In one-step methods like Euler's method, Morgan methods, etc. I mentioned an M file, timestep.m, to get a general idea as to how a time-stepping method should be could be coded. Although I want to make sure that did I actually post that file. Oh yes, it is there. So if you take a look at that, you can use that as a framework for implementing one-step methods in general, or it's like a lower order method like Euler's, higher order one like RK. Okay. So since we've just been seeing one-step methods, now we're going to look at the opposite of that, multi-step methods. Okay. So in one-step methods, what you do is, during each time step, you're at time tn, you've computed a solution up to that point, and you want a solution at time t n plus 1. And one-step methods use information about the solution and its time derivative only between those 2 points in time. So the way that you get higher order accuracy using a one-step method, as I just showed you when covering longer-cut methods, is you just evaluate your time derivative f from your ODE y prime equals f several times. Like RK4, there's 4 stages, 4 evaluations of f. But it turns out that it's actually not necessary to carry out that many evaluations of your time derivative during every time step just to get higher order accuracy. So higher order accuracy is possible with less, and the way you do that is with what's called a multi-step method. So here is a general form of a multi-step method. So we have 2 summations. On the left side, we have linear combination of y values, so solution values at different times, and coefficient of the linear combination are these alpha i's. And then on the right side, we have linear combination of your time derivative values. So f evaluated at select times and select solution values. And we have these coefficients of beta i's to combine them. Now the number m here is the number of steps in the method. So if we have m equals 1, that's just a one-step method all over again. So we're interested in the case of m greater than 1. So notice the solution values that we use, y, n plus 1 minus I. So when I is equal to 0, we have just y plus 1. That's what we're trying to find. If I equals 1, then we have yn. So that's our previous solution value. So for one-step methods, that's all we use. But for I greater than 1, we're reaching further back in time. So we're using older information to get higher order accuracy more efficiently. Now, I want to introduce some notation that I use that's commonly used in multistep methods. Because notice for every time I evaluate f, I evaluate some t-value and some y-value, but notice that the t-value and the y-value always have the same index. So it's common practice to abbreviate this evaluation of f. We call it f sub k, which is a function f evaluated at tk, yk. Again, if it's the indices of t and y being the same. Now, so the benefit of a multi-step method is that when we're evaluating f, we only have to evaluate f once each time step. We're mostly using f values from earlier time steps, and we already worked those out. So there's only one new evaluation each time step. So the result is that multi-step methods are more efficient than one-step methods. So take RK4 for instance. RK4 evaluates f 4 times every time step at different t values, t and y values that were not used before. But as we'll see, you can get a fourth order accurate multi-step method that only evaluates f1 each time step. So right away, your time steps are a lot cheaper computation than in a one-step case. But here's the drawback. You can't use them immediately. Like when you're at time 0, your initial time, you need values further back in time, and you don't have them because you can't do anything with solution at an earlier time. So what you need are called starting values. So first you go ahead and use one-step method. So for whatever value of m you have, you need to use a one-step method m-1 times. That gives you, so then you build up enough values so that you can have enough information to carry out the multi-step method. So for example, in the case of m equals 3, so you have y0, that's your initial data. So you use a one-step method to get y1 and y2, and then your what your multi-step method will do is it will compute y3 using y2, y1, y0, because for a n equals 3, a 3-step method, you need 3 previous values. So you just need a one-step method to get m-1 power, whatever n is. Okay. Now, with one-step methods, we saw that we had both implicit and explicit. It's very easy to tell the multi-step method is implicit or not. So if a beta naught, so the first beta on the right side, if beta naught is 0, then it's explicit, otherwise it's implicit. If you do have an implicit method, then just like with one-step methods, you need to carry out some iteration to compute yn plus 1. So really what you're doing is, you're trying to find a root of this function, capital F, of y. And what I've done here is I've taken this multi-step method, and wherever I had yn plus 1, I just call it y, with no subscript. And then I move this summation to the left side so that I have one expression equal to 0. So using some iteration to find a root of this function, we're working out carrying out an implicit method. But just like with one-step methods, you have a reasonable initial guess. You can just use yn, for instance, or you can use an explicit multi-step method to get a good initial guess for yn plus 1. So this is the general idea behind multi-step methods. But I realize that at this point things are still quite murky. But what I'm going to do now is focus on a particular category of multi-step methods. These are called Adams methods, named after John Couch Adams. Okay. So if I take my ODE, y prime equals f of ty. And then I integrate both sides of this equation on this interval. Then what I get by fundamental theorem of calculus is I have this integral form of a solution to my ODE. So this right here, this is exact. But it's not practical to try to evaluate this integral because I know this solution value times Tn, but this integral depends on the value of the solution that I don't have yet. I don't know what to plug in here. So the idea behind Adams methods is to approximate this integral. So what we do is, since this integral is with respect to s, but s is playing the role of the time variable, going from Tn to Tn plus 1. So what I do is I use a quadrature rule using various time values. Another way of looking at it is I'm approximating this function, f of s, y of s, with a polynomial, and I use these interpolation points. So Tn, Tn minus 1, Tn minus 2, and so forth, all as far back as I want to go. Now that's if the method is explicit. If the method is implicit, I also use Tn plus 1. So the idea is I'm using these as my input values into this function, and my outputs for my interpolation are the y values that I'm dealing with. And I will show you a little bit how one of these Adams methods is derived using this approach. Now, in all Adams methods, the alphas are laid out for you. And we only have two non-zero alpha values. So alpha 0 is 1, alpha 1 is minus 1, and all others are 0. So in this general multistep method form, the left side of this equation for Adams method is always yn plus 1 minus yn. That's fixed. Where Adams methods vary is what's happening with these betas over here. Okay, if beta naught is 0, then again, that's explicit, so those are called Adams Bashforth methods. Otherwise, we have implicit methods that are called Adams Moulton methods. I should mention that Bashforth had nothing to do with the invention of Adams methods. It was all Adams, but Bashforth was a number of scientists, like not even mathematician, that Adams was collaborating with. I guess the application key for Bashforth. That's how they got attached to it. Whereas Moulton recognized that explicit and implicit methods could be used together in what are called predictor-corrector methods, which I'll show you later. So he didn't really have a hand in developing implicit Adams methods either. So it's funny how people get their names on stuff about it. Like, did I do that? I mean, I actually haven't done stuff. My name's on anything. Okay. So I'm going to show you how a three-step explicit Adams method is derived. So that's the Adams Bashforth method of m equal to 3. So using these conditions that all Adams methods satisfy, this is a general form of a three-step Adams Bashforth method. So y plus 1 equals yn plus h times this combination, where the coefficients beta 1, beta 2, beta 3 need to be determined. So I define P2 of t to be an interpolating polynomial that fits this function at these time values. So I have, because I have a three-step method, I need 3 time values, starting from Tn and working your way back. So that's how we end up with Tn, Tn minus 1, Tn minus 2. So then I write my interpolating polynomial in Lagrange form. So no last semester we saw in polynomial interpolation using the Van der Waals matrix, and then Lagrange form, and then Newton form. But what we're trying to do here, we're designing an approximate integration scheme. Lagrange form is most suitable for that. So now, this integral that comes from my exact solution that I'm trying to approximate is approximated by the integral of this tripling polynomial from Tn to Tn plus 1. But then what I do is I make a U substitution. U is, by this formula here, the purpose for this formula is I'm mapping the interval Tn to Tn plus 1 to the interval 0 to 1. So Tn plus 1 corresponds to 0. Tn corresponds to 1. And the reason why I'm doing that is it simplifies working out these coefficients, the betas, because now instead of interpolating at Tn, Tn minus 1, Tn minus 2, now I'm interpolating at the integers 1, 2, 3. So now I'm going to work out this integral with the now it'll give me my coefficients. Now, when I'm working out this integral, I fill in the form of the Lagrange polynomial, interpolating at 1, 2, and 3 for U values. Here, and here, I filled in what the Lagrange polynomials are. That's something that's covered last semester, do chapter 7. And then I go ahead and integrate all three of those Lagrange polynomials. So, so we keep in mind that this right here is supposed to correspond to this summation right here, h times the sum of my betas times my f values. So if I work out what the integral is, I'm going to see these f values. I already have them. I already have this factor of h. So what that means is, okay, so I'll point it out again. Actually, I'll go ahead and fill it in. This whole thing is supposed to be equal to a sum from 1 to 3 of with the h on the outside. Beta I f m plus 1 minus. Okay, so this one I'm supposed to get. And you can see if I match this summation, actually I'm gonna write it not in sigma notation, but just write out each term. Beta 1 fn plus beta 2 1 plus beta 3 minus 2. Okay. So again, so just matching this whole expression against this, you see the h's match up, the f values match up. So the only thing left in this expression are the integrals, so these Lagrange polynomials. Those are the betas. So I go ahead and work out the integrals, and I get my betas. So 23 over 12 minus 16 over 12, 5 over 12. One thing that you can see here is if I add up all these coefficients, I end up with 1. So that's something that's true in general of Adams methods. So this is my 3-step Adams Bashforth method. So in contrast to Euler's method, where I just have y plus 1 equals yn plus h fn, now I have a linear combination of fn, fn minus 1, Fn minus 2, where the weights of this linear combination all sum to 1. But by using these values further back in time, I'm able to get higher order accuracy than I would with Euler's method. So speaking of order accuracy, so an m-step average batch-forth method has mth order accuracy, so the error is proportional to h to the m. So this method right here, this is a 3-step average batch-forth method, it's third order accurate. Whereas in the implicit case, the average multiplicity method with m steps, the error is h to the m plus 1. And the reason for that is, in the implicit case, you have an extra interpolation point at time tn plus 1. So your interpolated polynomial is of 1 degree greater. So it gives you an extra degree of accuracy. Yes?
That expression where you set it equal to h times, beta.
Yeah.
Isn't it like approximately equal?
Oh, the approximation happened earlier. Yeah, this is what we wanted exactly. We approximated by this, and then after that, it's exact, or no additional error. Okay, so questions about how we get a Adams method. Actually, now the way to get an Adams method is looking at Wikipedia. So you can see all the coefficients for various values of m, or at least as high as like maybe 6 or 7. Okay. Now, when you have an implicit method, and like I mentioned before, you can use iteration, like maybe use something like 6-point iteration to carry out a time step, and you have a convenient initial guess. But it's also quite common to use implicit methods in a different way, using what's called in the framework what's called a predictor corrector method. So in order to not have to use the iterative method, the predictor corrector method uses out of batch form and out of multiple methods together. So here's the procedure. That's abbreviated PECE, predict, evaluate, correct, evaluate. So what you're doing is, you first use your predictor, which is your explicit or Adams batch form method, and you compute a y plus 1 value. I'm calling it y plus 1 tilde because it's actually an intermediate value. It's not going to be our final y plus 1. But then we take that intermediate value and we substitute it into f with a corresponding time value tn plus 1. And we have this intermediate f value, so f tilde n plus 1. Then we use the corrector, the Adams multiplicity method. Now, normally, this has to be used as an iteration because we don't have a yn plus 1 to plug into f to get fn plus 1. But we can use this value instead. So we can use an implicit method as if it was an explicit method because we already have the values we need. And that gives us our final value of yn plus 1. And then we substitute that yn plus 1 back into f. And this gives us our final f value to use for the next time step. So no iteration required. So as an example, suppose I want to use a 2-step Adams multiplicity method, but in a predicted corrector form, so a conjunction of 2-step Adams batch form. So this is the explicit method. So I go ahead and I have fn, I have fn minus 1 from previous time steps. So I go ahead and work this out. I have my yn plus 1 tilde value. Then I plug it into f. I get my tilde fn plus 1. And now this is my 2-step Adams multiplicity method, the implicit method. So normally you have fn plus 1 here, but you don't normally have it. But I do have this, so I substitute it in here. Yeah, there is some error in there, but there's error anyway. If I work out this, I get my y+1 value, and so now my solution is up to date. Then to set up the next time step, I don't want to use this fn+1 value next time because this is out of date. I have a better y value now. So I substitute that in here. Okay, one thing I want to mention about order of accuracy. I want to make sure I'm not giving you something that's erroneous. Oh, okay. I have a, unfortunately, incomplete list of mistakes that have been found in the text. Okay. So, where were I? I'll talk more about convergence analysis in the next section, but there's a theorem here, so that gives in the next section. That gives the accuracy of m-step predictor corrector method. So if you're using this explicit method of predictor with this implicit method as a corrector, the error involved is a linear combination of the error that comes from the corrector and also from the predictor. Although this formula is slightly wrong, but this term needs to have an extra factor of h in it, so on the list of mistakes that I posted. What that means is when you're using multiple methods in combination, it's important to make sure that they have compatible order of accuracy. And I'll just make a note of that here. Okay, so so there's a couple of instances I want to talk about where it's important to check on the order of accuracy of methods you're using in combination. So first, if using a multi-step method, with the H of P order accurate, P order accurate, you have to make sure your one-step method that you use to generate starting values that has at least as much accuracy. Because, for example, suppose we're using, say, a four-step threshold method, four-order accurate. Good idea is to use RK4 to generate the starting values. If I used Euler's method, for example, generate starting values, that's very convenient. But in you have first order error that taints your first solution dies. And even though you're using a fourth order accurate method after that, that first order error doesn't die out. So, so if you use a lower order accurate method, that affects your solution forever. So, so make sure that your starting value method is at least as accurate as your multistep method. Second, the predictor corrector method use the same number of steps for a predictor and a corrector, because the overall error comes from the error of a corrector plus h times the error from a predictor. Now, a predictor is the adversarial method that is order h to the m accuracy. You multiply that by h to get h to the n plus 1. The error of a corrector already is order h to the n plus 1. So if you use the same number of steps, then your combination, your overall predictor corrector method will be m plus first order accuracy. So when these orders of accuracy are out of balance, then you're being wasteful in some sense. Now, Adams methods are only one kind of a multistep method. There's another kind that's actually quite effective called backward differentiation formulas, or BDFs. BDFs are always implicit. So with Adams methods, the alphas are fixed and you have to figure out the betas. With BDFs, it's the opposite. There's only one non-zero beta value, beta naught, which is, well, depends on what source you use, but tends to be normalized so that's equal to 1. And then you need to figure out the coefficients on the left side, the alphas. And again, by analogy to Adams methods, you figure out the betas for an approximate integration, a quadrature rule. With BDS, you work out the coefficients of the alphas. They're coefficients of a finite difference formula for a backward difference, which is where our gain comes from. So all BDS can be written this way. And I think this formula, yeah, I need a factor of, I think 1 over h in here. I need to check this here. Ah. Okay. Check this was what happened to text here, because again, there's another issue with mistake. I want to need to make sure my notes have the right thing. Okay, yes, this is the same formula that's in the notes, but this formula is wrong. There needs to be a factor of h right here. So we'll go ahead and put that in. So just as in the Adams methods, your betas are the integrals of Lagrange polynomials. Your alphas here come from derivatives of Lagrange polynomials. And since we want to approximate the derivative of y at time t n plus 1, that's the value we plug in to the derivatives of our Lagrange polynomials. Another formula for these alphas is a little simpler. Make a note of that here. I equal to minus run polynomial at 0, where these are run polynomials. Polynomial of u. We can see between the variables in Adam's case. Polynomial for points 1, 2, up to n plus 1. So by making a change of same change of variable where you map the interval tn to tn plus 1 to the interval 0 to 1. So this point tn plus 1 is mapped to 0. Because of the minus in that change of variable, we end up with a minus out here as a result of the chain rule. And the h ends up being canceled out. So there's a nice analogy here with again with atoms versus PDF. So the atoms, betas are the integrals with Lagrange polynomials, interpolating at 1, 2 up to m, or okay, or 0 to m for the implicit case. Oh, sorry, I goofed here. This should be 0 up to m, not 1 m plus 1. Yes, so for an implicit Adams method, Adams multi method, you're integrating Lagrange polynomials for points 0 to m. For BDFs that are all implicit, we're taking derivatives evaluated at 0. Same interpolation point 0 to m. So the same Lagrange polynomials that would be used for an Adams multi method. Just because Adams methods work with the integral form of the ODE, whereas BDFs work with the original differential. M-step BDF is an M-order accurate. But if you go too high with M, you get a method that is called unstable. I haven't talked about what it means for a method to be stable yet. That's actually the subject of the next section. But what it means is there are only 6 PDF methods. And I guess the simplest one being the upper backward loader or traps loader. So all possible PDF methods are listed on the Wikipedia page. You get all the coefficients. Well, all ordinary PDF methods. Should mention that BDFs. Oh, signature on page. Oh man. Okay. Now, stiffness is a concept I'll be covering soon, but for now, I would say those are more challenging ODEs to solve, are ones that are stiff. And BDF methods have very good properties that make them useful for these kind of problems, even though they can be expensive because they're explicit. Whereas some of MATLAB's non-stiff ODE solvers will use Runge-Kutta methods. So that's the story on multi-step methods. So, do you oodle some time questions about anything, homework? And you think you'll do the coding option for a while? Okay, it was definitely no bear, I guess. Yes, it's usually the less chosen option. All right, so I have an early lunch.